One of the most important applications of the cross product is the concept of torque in physics. And I think this is a really great example, just in general, to build intuition for what the cross product is really doing. So let's say we've got a bolt with threads like this, and we're turning on this bolt with a wrench. So we have this wrench, and then so we're turning on this wrench, applying some force to it. So this is going to be driving the bolt forward into the wall, and we'll call this the torque produced, this force, the torque produced on the bolt by the wrench action. So the torque should be orthogonal to both. Let me call the vector of our lever arm r. The torque should be proportional to both of these and also orthogonal to both of them. So for example, if you were applying like the torque you want to be going straight into the wall, if you were applying your force parallel to the torque, that would mean you'd be pulling the wrench entirely off the bolt, either forwards or backwards off the bolt. So it wouldn't be producing any force forwards. So that tells us about the direction of the torque. Then we need to know the magnitude. Well, so we want to find the component of the force. We need to find the component of the force that is orthogonal to the lever arm. Again, if you were applying your force parallel to the lever arm, that would mean you'd just be pulling in the direction of the wrench. So that, again, wouldn't be doing anything, or pushing in the direction of the wrench, which wouldn't be turning it forward at all. So this length here, this orthogonal component, if we call this angle theta, that'll be length f sine theta. So the torque that we're after will be length r, length f, sine theta, and then this times a unit vector. And so the magnitude of the torque will be length r, length f, sine theta, and then times a unit vector like this. And from what we've seen, this is exactly r times f. Now, this theta here, we have to be a little bit careful. So the vector theta or angle theta between vectors f and r, that's going to be this angle, because r, like we need to move r forward to start at the same point as f in order to compare the angle between them. So here we're really taking sine of 180 degrees minus theta if we want theta to be the angle between r and f. But that's okay, because we have for any angle sine 180 degrees minus theta is sine of theta. So we can interpret theta either as this angle here or this angle here, and it doesn't affect the formula. So in summary, whenever we have a force F acting on a lever arm R, their torque we define to be the cross product R cross F. And then in this context, the right-hand rule is interpreting that we turn clockwise. So the right-hand rule is saying if we are curling from R in the direction of F, which, so that will be going from R into the direction of F will be clockwise. And so yes, turning our convention for bolts is that turning clockwise will screw it in, and turning counterclockwise will screw it out. So let's say, for example, we have a 5-foot lever arm. We apply a force to that of 30 pounds. The angle between them is 40 degrees. And we're asked, what is the magnitude of the torque produced by this twisting? And so our answer will be, so that's the length r times magnitude f times sine theta. So this will be 5 times 30 times sine 40 degrees. This is approximately 0.64. And so we get, this is approximately 96.42 pound-feet.